Welcome to our video on regression and correlation. So this is following on from our graphing rules. And we're going to be talking on this one mostly about scatter plots. And one of the things that a scatter plot is good at doing is allowing us to make predictions. So we are trying to find the relationship between two things, and that's why we graph. You can do three variables where you're doing wireframe plots and 3D models and the like. But generally we're doing two variables, in this case cucumber yield versus rainfall. Okay, and we want to know whether rainfall makes a difference in cucumber yield, and we want to know whether if we're going to get if we get a lot of rain, whether we're going to expect to see more, we'll be able to get more crops or not. So we want to be able to find out what the ideal amount of rain is for growing cucumbers. So we look at a scatter graph, and we can add lines, and we see whether there is a correlation between cucumber growth and rain. So it may be that the rainfall isn't the thing that causes this positive relationship, as you know, like where there are more cucumbers per meter squared when you have more rainfall. But that's a pretty strong relationship, and so we can say that there's probably a causal relationship, but we can't say for sure. That's correlation. Here we go height versus weight. So you'll get some people who are very short and not very heavy, but you can get other people who are short and a lot heavier, or tall and not very heavy. But in general, as height goes up, weight will go up as well. And for us men, hair decreases as time goes on. You get a few people that are quite hairy, even though they're old, and you get some young baldies. Okay, but hair, that's a negative correlation. This one's a positive correlation, a negative correlation. And then here you have eye color versus age. So your age doesn't change your eye color at all. Your eye color is what it is. And so there's no correlation between your age. It doesn't change after you're about 6 or 8 months old. And the great thing about being able to put a correlation or a line of best fit, one of those lines on our scatter plot, is we can use it to make forecasts or predictions about what might happen. So if we, for example, own a surf shop and we want to know whether the water temperature is going to increase or decrease wetsuit sales, or how many wetsuits we should expect to sell if the water gets really cold, we can go ahead and graph that and then see what happens. In this example, we should expect a decrease in the seawater temperature to mean that we'll sell more wetsuits as it gets colder. And so if you go to the end, the questions on page 33 in your workbook on regression and correlation, you should work through the questions there, and then we'll carry on. Okay, you worked through the examples. Now, what are you going to do? You're going to draw a scatter graph, as we've seen. And in most situations, we're wondering whether which one of the variables will affect the other. In this case, we're talking about whether the water temperature affects wetsuit sales. We're not gonna think that because we've sold more wetsuits, the water temperature is going to go up or down. The wetsuit sales shouldn't have any effect on temperature. So the independent variable, the explanatory variable, water temperature, the one that explains the other variable, variation, should go on the x-axis. And the response variable, or the dependent variable, goes on the y-axis. So we're saying that wetsuit sales depend on, or are dependent, they depend on water temperature. So the dependent variable goes on the y-axis. And if you're not sure which one affects the other, then, and which can happen. I'm not going to give you an example right now, but you can put either variable on the x-axis. And we have two things. We have regression, which is the line, and then correlation is the strength of the relationship. So the regression, it tells us what the pattern of the relationship between the two variables is. Is it positive, negative, or no relationship? And then correlation tells us how strong it is. As we said, the regression describes this line that is the pattern between, that is the relationship between the two variables. So we have y, which is any value on the y-axis. Okay, this is the y-axis. So it depends on what you put in for x. X could be any number that you like. So we're trying to find out what will happen if x is, say, 3. So we have c, which is the y-intercept. And if we know that the equation is y equals 5x plus 10, then c, or 10 here, is where we start the line on the y-axis. And then we know that the slope, m, which is 5, means that for every 1 that we go over, so if we go over 1, we go up 5. So you see that in this case, a credit card company charges $10 when a payment is late, then $5 per day when the payment remains unpaid. So we've gone 1 day over, and we've gone up by $5. So if you have 1 day right here for the value x, of which is 1, you have the value of y equals $15 per day, or $15. So that's what you're going to get charged if you have if you're a day late. You get $10 automatically, and then $5 for that day. If you're going to go over 2 days, then you're going to wind up paying $20. 3 days, 25. 4 days, 30, etc. So that is the slope. It goes up by 5 for every 1 that it goes over. Okay, so that tells you what the slope is, and this will allow you to know for any value of y what you'd expect x to be, or for any value of x what you'd expect y to be. So just another note on that, since we know any value of x, let's say if we know the water temperature in that last equation was 14 degrees, then we should be able to figure out what y is, or how many wetsuits we can expect to sell. Now, we go to correlation next, which tells us whether that expectation is a strong expectation or a weak expectation. Is it a good relationship based on our data, or should we expect that is maybe a bit of a squidgy prediction that we can't really rely on that much? And so we use this thing called R, Pearson's correlation coefficient, and it tells us whether it's a strong relationship or not a very strong relationship. So if we have a positive correlation, then our R will also be positive. It's 0.4, so that is a positive relationship, a positive number, not a negative. So if we have no correlation, our R should be around 0. And then if you have a negative correlation, where as whatever this value is, x goes up, then y goes down. So that is called a negative correlation, and you'll have a negative number, negative 0.04 there. Okay, so that indicates that's the direction of the relationship, is the negative and positive. And if you have r squared, the higher this number is, the closer to 1 it is, then the stronger the relationship. So we're going to draw a line of best fit. It's going to go right through the middle of that, and all the values are very close to that line, which means that this line that we drew is a very strong predictor of what we're going to find if we know one variable. So if we know that this x variable is 6, we're going to be pretty confident that our value is around 21 or something like that. So it's a small range that we could will find within our predicted. If we know the x if we know the x variable will have a small range that the y will fit in. That's a strong relationship. And if our dots are spread out a little bit longer, our plot points for our individual measurements, then our range is getting bigger, and we could expect that our prediction here isn't going to be quite as accurate necessarily for any individual measurement. So if this was water temperature again, and you had 6 degrees, you'd be much less sure of how many wetsuits you're going to sell. It could be anywhere from here to here. Whereas this one, you're sure it's a smaller range. You're going to have much less variation in how many wetsuits you sell. And then here, you may have exactly the same line of best fit, but here we're going to have a really big range. So knowing that the water temperature is 6 degrees, it's really not that helpful in predicting how many wetsuits we're going to sell. And that's where we have a very weak R squared, which is 0.1. That's a weak correlation. Okay, we'll just reiterate that with this example again. So if you have a very strong relationship of 0.86, okay, it's a strong positive link between the two variables. So that means the more the temperature drops, the greater the number of sales. Okay. So here would be our equation. 0.86 squared equals 0.74. So we square the R value to get the correlation coefficient, and that gives us a percentage. So 74%. All right, we're not going to go into why we square it, but just trust me on that, or you can look it up or ask me in your own time if you want to know the mathematical reason. 74% of the wetsuit sales can be explained by the decrease in the temperatures. So 74%, if you have a correlation coefficient of R squared of 0.74, that means that 74% of whatever happens to that variable on axis y is explained by whatever happened to the variable on axis x. The 74% of what we see on the dependent variable is due to the independent variable. So you never know. There's 26% that could be blamed on economical circumstances, or whether there's a surf contest in town or something like that. It doesn't tell you everything about why the y variable varies, but it may give you an indication. And p-values, which we're going to get to next week when we talk about hypothesis testing. If we're doing two continuous variables, then we're not going to be doing a test like a t-test or an ANOVA. That'll become a little more clear later. So you just report the R squared value when you're doing a regression and correlation. You can generate a p-value, but don't use p-values when you're reporting regression and correlation. And finally, I have a couple of recommendations. They're on the PowerPoint. If you download that, these hopefully will help you understand the concepts of regression and correlation a little better with some animation. Okay, cheers.